Hello friend, welcome to ashatech.com. We continue with our revision questions, particularly for composite bars and the other related questions in mechanical engineering science. Question 1, the guiding question says, explain the following as applied to loaded materials. 1. Stress. 2. Strain. Modulus of elasticity. Part B says a steel cylinder whose outside and inside diameter is 0.5 meters and 0.45 meters respectively is 1.5 meters long. It is filled with concrete and used as a vertical column to support a weight of 30 kilonewtons. Determine part 1, compression and the stresses in both steel and concrete. Part 2, extension in both components. Let's go ahead and answer these questions. Okay, stress refers to the load per unit area. That is Roman 1. Load per unit area, it means this is a load over area, and this is maybe in kilonewtons per square meter, and it can be given as sigma. Then what about strain? Strain is the change in dimensions per the original dimension, such as if we are talking about direct strain and in terms of length, then it means a change in length per the original length will give you what we call strain. This is equal to the change in length divided by the original length, and it has no units because it is the ratio of two quantities of similar units. What about modulus of elasticity? Is the ratio of stress to strain. Therefore, E is equal to stress over strain, and therefore this one can also be in kilonewtons per square meter, but majorly we find that it is in giganewtons per square meter. Let us look at part B, where we have a component made from steel, a tube whose inside diameter, internal diameter DI is 0.45 meters and outside diameter is 0.5 meters. If it is filled with a concrete, this is concrete, and later on made it support a weight of 30 kilonewtons. So if it supports a weight of 30 kilonewtons, it means it will experience a reaction equivalent to 30 kilonewtons also. Now to proceed here, we have to find the area of steel, and the area of steel is equal to pi out of 4 times outside diameter squared minus pi out of 4 times diameter of internal squared, and this is what will happen. Substituting the values, internal diameter is 0.45, outside diameter is 0.5, so pi over 4 into 0.5 squared minus 0.45 squared will give you 0.37 square meters. What about area of concrete? AC is equal to pi over 4 times the square of internal diameter, because concrete fills the internal. Therefore, this will be pi over 4 times 0.45 squared, and this will give you 0.159 square meters. What about total area? Total area will therefore equal to 0.37 plus 0.59, and this will give you 0.196 square meters. What about the modulus of elasticity of steel? We have it as 200 times 10 to the power 9 Newton per square meters, and the one for concrete is not given, so we have to assume. It. So let the modulus of elasticity of concrete be 1 over 20, or a 20th of that one of steel. And of course, usually the modulus of elasticity for materials like steel is less, so much less than that I mean, for materials such as concrete is always so much less than for materials, for example, steel. Therefore, 1/20 of ES will give you 200/20 times 10 to power 9, and this would give you 10 times 10 to power 9 Newton per square meters. So having gotten the modulus of elasticity of steel, we have to now find the force that is withstood by steel. So Fs is equal to Es. AS, remember, the combination of steel and concrete later on to support that weight will mean that is a composite bar or a composite component, because it comprises of different materials, steel and concrete. Therefore, the weight that is going to be withstood by steel is going to be ES. AS times the total weight divided by the sum of the product of modulus of elasticity and area of the different materials. Therefore, substituting in would give 200 times 10 to power 9 times 0.037, which is the area of steel, times the total weight, which is 30 kilonewtons, divided by 200 times 10 to power 9 plus 0.37, plus that is now modulus of elasticity of concrete, 10 times 10 to power 9 times 0.159, which is the area of concrete. Therefore, that force would give you that one, substituting in and simplifying, would give you 24.69 kilonewtons. We move ahead. So if we use equilibrium conditions, we realize that this total weight is held or withstood by the different materials, that is concrete and steel. Therefore, if we know the force that is taken up by concrete, I mean by steel, then we can get that one taken up by concrete. This will be 30 minus 24.69, because the total weight is 30 and the force of the force taken up by steel is 24.69, which would give you FC equal to 5.31 kilonewton. Okay, let us find stresses. Let us find the stresses. The stress in concrete, sigma C, will be equal to the force divided by area. So for steel, I mean for concrete, it is 5.31 times 10 to power 3 divided by area, which is 0.159. It is equal to 33.4 times 10 to power 3 Newton per square meter. What about stress in steel will be Fs, or force in steel, force for steel divided by cross-sectional area of steel, 24.69 times 10 to power 3 divided by 0.37 would give you 667.297 exponent 3 Newton per square meters. And so we have to look for the compressions, because if this weight is supported by that compound component, then we need to find the respective compressions undergone by concrete and that one undergone by steel. So we know that the stress in steel, I mean the extension or the compression, actually the change in length of steel will equal to the stress of steel times length divided by the Young's modulus of steel. So this is the stress in steel is 667.297 times 10 to power 3. The length of the whole component or of steel itself is 1.5 divided by the Young's modulus 200 exponent 9, which would give us 5.0 times 10 to power negative 3 millimeters, and this is the same as 5.0 micrometer. What about the compression for concrete? It will therefore equal to the stress in the concrete times the length of the concrete column divided by the Young's modulus. This is 33.4 exponent 3 times 1.5 divided by 10 exponent 9, and this will also give you 5 exponent negative 6 meters, and this would give you 5.0 micrometer. Now for us to find, for part B, for us to calculate the extension or the compression in the component as one, or what we call the common extension, then we are going to use the formula for combined modulus of elasticity, EC, is equal to the sum of the modulus of elasticity of the different components times their respective areas divided by the total area of cross-section of the different materials. Therefore, if I expand this, it will be that one modulus of elasticity of steel times cross-section area of steel plus modulus of elasticity of concrete times area of concrete divided by area of concrete plus area of steel. This would give you 200 times 10 power 9 times 0.37 times 10 to power plus 10 times 10 power 9 times 0.159. These are components, this is the information for concrete, divided by 0.037 plus 0.159, and the combined Young's modulus or modulus of elasticity would give you 45.87 times 10 power 9 Newton per square meters. Then the stress, therefore, in the equivalent bar would be the total weight the whole bar holds divided by the total area of cross section. If the total weight is 30 kilonewtons, then the total area is 0.037 plus 0.159, and this would give us the stress in the equivalent bar of 153,061.225 Newton per square meter. What about strain in the equivalent bar? It will therefore equal to stress out of Young's modulus, because we know Young's modulus is equal to stress over strain. Therefore, substituting in that formula, our strain would give us this. Now put in the information for stress. We have also for combined modulus of elasticity, it would give us 3.337 times 10 to the power negative 6, and it has no units because it is the ratio between quantities of the same units. This will be that. What about now the common extension? The common extension, we know that strain again is equal to the extension divided by the original length. We are saying that the strain is equal to the extension divided by the original length. So if we want this, we just cross multiply. So this will equal to strain times original length. So if we substitute in original length is 1.5 meters times strain, which is 3.337 times 10 to the power negative 6, it would give us 5 times 10 to the power negative 3 millimeters, which would give us 5.0 micrometer. Thank you so much for watching. See you next time.